everybody. In this lesson, we're going to talk about electron configuration. So we went over electronic structure last lesson. Now we're going to how do we represent what each element's electronic structure is. Well, the big idea here is that electronic structure can be represented by specific notation that represent the electron configuration. So how do we use electron configuration to represent electronic structure? Well, first of all, we do not need to draw an energy diagram. Instead, what we use a notation to fill electrons. And what this notation is it uses superscripts and orbital letters to show where electrons reside. So if you remember this image from last lesson, you would remember that electrons fill in this order, and that's how it relates to the periodic table. So because it goes 1s, 2s, 2p, 3s, and so forth, you will see that the fill order goes in this order right here. It goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 6s, or 5p, 6s, and so forth. Well, if you want to continue, it would be 4f, 5d, 6p, and so forth. So you use that periodic table to help guide you. Based on where the element is, it will always have the electrons before it. So now the second thing you want to know is how many electrons can fit in each of these subshells. S orbitals can only fit 2 electrons. That means if you write this, you have 2 electrons in the 1s, 2 electrons in the 2s. P-type electron orbitals can fit 6 electrons. So if this was fully full, it will be 2p with a 6 exponent. And I'll show you what that looks like when we start writing. So what we want to start off with is we look at where the element is on the periodic table. And from there we can find number of electrons. First step, we fill electrons from lowest energy first. Second step, we fill until we use up all the electrons. And third step, all superscripts, aka the exponents, should add up to the number of electrons. So let's practice. So hydrogen. Hydrogen only has 1 electron because it is in the top left corner. It has 1 proton as well. Where does that 1 electron reside? Well, if you remember, these right here are the s electrons. So in this case, hydrogen only has 1 electron. It resides in the 1s orbital. How many electrons does the 1s orbital have? 1. And this is the electron configuration of hydrogen. Let's take a look at lithium now. Lithium is right here. Lithium has 3 electrons. Well, lithium has 3 electrons, okay. Right here, these are the 1s electrons. That means if hydrogen helium were to be there, it'll have electrons in the 1s. Lithium has, in this case, these are the 2s electrons. It has one electron in the 2s orbital and has two electrons in the 1s orbital. So to write that one, we write it as 1s2, 2s1. Notice that these numbers up here always adds up to the number of electrons. Okay, let's look at carbon. Carbon has a total of 6 electrons. Now if you look at carbon here, you will notice that carbon is right here. These are the p electrons. This is labeled as the 2p. So if you want to see this, you could see that this is labeled, as, let me close this, the 2p's. Okay? So in this case, because at 6, well, still fills, 2 electrons still go in the 1s because it's the lowest energy. Always want to fulfill the lowest energy first. The next 2 goes in the 2s. Now there's how many more electrons? There's still 2 more left. Those ones go in the 2p. Now if you look at this, you can see that carbon being right here, being that these are 2p's, there's 2 spots in which carbon's into. These are 2p's. Then you go backwards. These are 2s's, so it has electrons in this 2s orbital, and it has 2 more electrons in the 1s orbital. You could think of it as almost like a experience bar. The more electrons it has, the more experience it has, the more it has experience from the elements from behind. Likewise, if there's oxygen, oxygen will have 4 2p's, so 2p, 4. Then it also has 2s2 and 1s2. So that's where oxygen comes in. So just like what we said here, oxygen has 8 electrons, where 2 of them are in the 1s, 2 of them are in the 2s, and there's 4 more, and these are the 2p's. Okay, I'm still basing all this based on this picture right here, or on page 153 of the orbital energy diagram. That diagram shows you which one is the lowest energy. But I find that this one's much easier to see. Okay, let's try iron. Iron is a lot more. Iron has 26 electrons. Okay, so let's start with that. It has 26 electrons. Alright, so let's look at iron. Iron is in a region we call the 3Ds. This is the 3D orbitals. How many 3Ds? 1, 2, 3, 4, 5, 6. So iron has 6 3D electrons. But if you go back, iron also has 2 4s electrons. It also, if you're going back, it has 6 3p electrons. Keep going back, it has 2 3s, 6 in the 2p's, 2 in the 2s, and 2 in the 1s. So if you write this out, this is what it looks like. It has 2 in the 1s electrons, it has 2 in the 2s electrons, it has 6 in the 2p's, it has 2 in the 3s, it has 6 in the 3p's, and last but not least, it has 2 in the 4s, and it has, because we're here now, it has 6 in the 3Ds. Now note that these 3D electrons are not full, because the d orbitals could fit 10. If we now look at neon, we see that neon's right here. It has, in a sense, 2 in the 1s, 2 in the 2s, and 6 in the 2p's. So this would be neon's electron configuration. So that shows you what the electrons go, where each electron goes. But how does it relate to Bohr model? Because if it could relate to Bohr model, it makes a lot more sense. You remember in Bohr models, the fill number was always this. You had 2 electrons, then 8, then 8, then 18. That's still here. If you look at it here, you will see each shell is always the same energy level. So if you look at, for example, let's look at iron. Iron, the first shell, which is the first energy level, has what we see is 2 electrons. The second shell, which is the 2 energy level, has 8 electrons because it has 8 total electrons there. The third one has also 8. So you see how if you add 2 plus 6, it'll be 8 still. So you notice that it doesn't actually change. It's just that we're giving these. So in board model, we used to just say all these are exactly the same, but now we're giving them names. So if you look at our board models we drew last lesson, for example, let's look at, for example, carbon here, or let's look at chlorine here. You would see that in the first here, these are your, in this case right here, these are your 1s electrons. Right here, these are your 2s. Then these 6 right here are your 2p electrons. Next orbit, these are your 3s. These are your 3p's. So that's how this works if you relate it back to the Bohr model. Now, what are some issues with writing electron configuration? Well, one of the big issues is, let's look at, for example, I don't know, let's look at uranium. If you notice, uranium has 92 electrons. That will take a long time to write. So one of the biggest issues is it is tedious for large elements. So what we solve it is we have a quicker way. We can make this easier by using what we call core notation. So how does core notation work? Well, what core notation looks at is this. It uses only the electron configuration of the valence electrons. Hey, valence electrons are coming back. So what that means is it only cares about the valence electrons. But you also have to show what we call a fully filled core. So a fully filled core, aka it has a full shell. Now, which ones have the full shell? If you look at this periodic table here, which elements do you remember have full shells? The noble gases. These noble gases have full shells, so what we do is we show these by doing this. We use the noble gas as a full shell. So how do we write core notation then? To write core notation, it's the same as before, but now what we do is we start by writing the symbol of the noble gas in square brackets. And then what we do is then write the electron configuration of the valence electrons only. Okay? So only the valence electrons. But there are some restrictions. Let's say, for example, you're trying to write the core notation of argon. Well, if you just write the core notation of argon, you can't just put argon in a square bracket. You have to actually use the previous row's noble gas and then write the valence electrons for argon. Okay, so that is a little disclaimer. For noble gases, have to write previous row's noble gas. So let's practice this. If you look at uranium, this is the core notation of uranium. You might look at this and go, that is a gigantic mess. What is the core of uranium? Well, if you look at uranium on the periodic table, uranium is right here. Technically, uranium actually fits right here. So this is why the periodic table is like this. Because this section, which we call actinides and lactonides, actually fit right here. So if uranium is actually part of this row, what's the previous row's noble gas? It's radon. Radon has 86 electrons. So in this case, we look at this and we see that radon is actually this sequence right here. Right here, this is radon. So that means whatever right here that I underlined in red, this is your valence electron. So what does a core look like? Well, you put radon, the symbol for radon, Rn, in square brackets, and then you write out the valence. Now we're going to get into why our core, our notation looks like this, because why is it that 7s is afterwards? Well, 5f3 is over here, and so forth. We're going to get into that in a bit. But let's practice this. Let's practice this by looking at what are some examples. Well, let's go oxygen. Oxygen is located right here. So to write the core notation of oxygen, we look at the previous role noble gas, which is right here, and that's your full core. So helium is right here. So what you want to do is you want to put helium in a square bracket to say that that is our fully filled core. Then we write what is in the valence electrons. So this section is still in the valence. What is this section? Well, here, this is the 2s electrons. So we write 2s, 2, because that is still in the valence. And then right here, we will write 2p4, because there's 4 electrons still in that valence electron. So 2p4. And this is, in a sense, the core notation of oxygen. If you look at iron, iron's right here. The previous row noble gas is argon. So we want to put argon in a square bracket. Then what we're going to have is now we want to look at what is in the valence electron, which is in this row right here. This section is called the 4s electrons. That's 4s2. Right here, this is the 3d. How many 3ds do we have? We have 6 more to reach iron. So we have 3d6. So you might notice this made iron a lot smaller and much easier to draw. Neon. Now neon, because of that exception rule we had, for noble gases, you have to write the previous row of noble gas. So you cannot, for neon, you cannot write this. This is not allowed. Instead, we look at neon, we go, what's the previous role of neon? It's helium. We gotta do that. We gotta still write and show the electron configuration. We still have to have electrons present. So helium ends up being, so neon ends up being 2s2 and 2p6. Now, there are some exceptions to the rule. The biggest exception is that there's something called fully filled and half-filled orbitals, because we know we always fill lowest energy first. But here's the exception. Fully filled or half-filled d orbitals are lower energy than filled s orbitals. So what does that mean? It means that s orbitals can transfer their electrons to d orbitals. So s orbital electrons can give electrons to d orbital to make full or half-filled. An example that would be, let's say for example we have chromium, Cr. Chromium, usually you'll write it as Ar 4s2 3d4. But what can happen is one of these s electrons can go towards the 3d, and we are now at argon 4s1 3d5. And this one is a lot lower energy than the first one, because a half-filled d orbital, which can hold 10 electrons, 5 being half, is lower energy than this. 2 electrons from the s orbitals can actually fully go over to the d orbitals, which is why sometimes the 4s electrons can actually, or the s electrons can actually disappear. Or not disappear, but can be fully transferred to d orbitals. So let's practice. Let's look at this. Molybdenum. Molybdenum is located right here. So if I write the core notation of molybdenum, we have krypton as its core. So we put krypton Kr. Then right here, next one, we have 1, 2, 3, 4, 5. So remember, you can actually count these s and p's by counting down. So here's the 1, 2s, 3s, 4s, 5s. Here's a 1p, 1. There's no p orbitals for 1, but 2p, 3p, 4p, 5p, and so forth. The d orbitals go 3d, 4d, 5d. So you look at this. This is the 5s electrons. You have 5s2. And how many d orbitals you have? You have 4d4. So what can happen now? Well, this d orbital can be half filled, because if this s electron just transfers just one electron over, it can become a lower energy state, which will become krypton 5s1 4d10. And this is the electron configuration of molybdenum. If we look at gold, for example, we will see that gold will be, in this case, going to be what? Well, gold is located right here. So xenon is its core. And right here, if we count it down, this is 1, 2, 3, 4, 5, 6, 6s right here. So those are the 6s electrons. 2 of them goes here. Right here, these are the f. How many f's? These are the 4f electrons. There's 14 of them. So we have 4f14. Lastly, let's look at the d electrons. There are 9 d electrons in total. So we have 9. In this case, it will be 5d9, because these are the 5d electrons. So again, the s electrons are like, hey, I could give you one of these electrons so that you can become stable. And when that happens, you get xenon. 6s 1, 4f14, 5d10. And that is a much more stable electron configuration than the first one. Now if we look at, for example, platinum. Platinum, because it's on the 5d8, will get 2 of these electrons transfer over to become 5d10. So that is the core notation of the following. But what about ions? Let's finish off our lesson about ions. To write the electron configuration of ions, you have the following. What you want to do is you add or remove electrons based on the ion itself. But there's a rule. Okay. Now we know that metals will gain electrons, or lose electrons, I mean. While non-metals will, in a sense, gain electrons. So, what will happen if you have different ions? What will happen? Well, for your anion, you just add electron to configuration. Just like you've had to do the last couple of whiles. But for cations, this is where it differs. You remove electrons in this orbital, in this way. P orbitals first, then s orbitals, then d orbitals, in that order. So let's see that as an example in a bit. So let's get nitrogen ion. Nitrogen ion means that you add 3 electrons, because nitrogen has a -3 charge. So what does that mean? It means that nitrogen, which is right here, gains 3 electrons to get a fuller shell. So its core is still helium. So its core is still helium. And this is what it would have been, 2s2 and then 2p3. But because it gained 3 electron, oops, that should be He, then it becomes He 2s2 2p6 because it gained 3 in the 2p's, same as before. Sodium ion, the core of sodium is neon. So in this case, it will be, if it was just sodium atom, it will be neon 3s1. But because sodium's ion is Na plus 1, it loses electron. So it loses this electron. When it does that, you're going to end up getting something that looks like this. But what do we know about writing the core as just the noble gas? It doesn't work. So you got to go down one more because you can't write just neon by itself. You got to write the previous row's noble gas, which in this case is still helium 2s2 2p6. So what does that mean? It means nitrogen ion and sodium ion will have the same core notation. Well, let's look at iron 3 ion. With iron 3 ion, the core, the initial core is argon. So it's argon. And it's 4s2 3d6. 4s2 3d6. Okay? Now with iron 3, what's going to happen is it becomes, if you remember this is Fe plus 3, it's going to lose 3 electrons. Where does it lose the 3 electrons? Well, it's going to start losing itself, first of all, from the p orbital. Are there any p's in the core? No. The next one's going to lose from is the d electrons. It's going to lose these 2. So that's 2 of them. But where's the last one going to be? The last one's going to come from the d electron. That's going to go down by 1. So what you're going to end up with is you're going to end up with argon 3d5. And that, if you notice, is the reason why iron 3 exists, because it's now a half-filled d orbital. What happens if I do this with iron 2, which is the other type of iron? If I look at iron 2 ion, which in this case is Fe plus 2, you're going to notice that it's, first of all, it's argon 4s2 3d6. In this case, it's going to lose 1 electron from here and another electron from here, so it's going to be 4s1 3d5. Because this is a lot more stable. So, make sure you complete the homework and do a lot of these practice. Make sure you remember, when it's a cation, you remove electrons from p orbitals first, then s electrons, then d electrons. As always, make sure you keep yourself safe and healthy, and I'll see you soon.